Now let's consider hypothesis testing where we are comparing two groups as opposed to one group to a target value. In the two sample means test, we are comparing the average of one group to the average of another to establish equality. Note the hypothesis statements here are framed for equality, or a two-tailed test. We could also apply this approach to a one-tailed test depending on the circumstances of the investigation and context. Independent treatment implies that samples from each group are obtained independently of another. The number of samples in each group need not be the same. The test statistic is based on the respective sample mean, sample standard deviation, and sample size of each group. The formula here assumes the variances between each group are not equal. Like before, a critical stat can be calculated based on students T with a designated alpha and degrees of freedom. Recognize, however, that the calculation of the degrees of freedom is based on a numerical relationship between the variances and sample sizes of each group. It is a rather complex calculation and is best left to technological applications to properly determine. A comparison is made between the test stat and the critical stat to determine our decision. If we establish the variances between the two groups are the same, our calculation simplifies immensely. We can pool the variances into one calculation and incorporate this value into the calculation of the test statistic. S sub p is the pooled standard deviation. As you can see, this simplifies the degrees of freedom calculation as well. Let's consider this example. Suppose we are comparing the average temperature of two freezers. We want to determine if the temperatures are the same. Assume alpha is 0.01. If we assume equal variances, the pooled variance will be 1.511. The degrees of freedom will be 8. The test stat and critical stat are 0.7975 and 3.355 respectively. Since the test stat is smaller than the critical stat, we fail to reject the null. Now consider the same problem assuming unequal variances. It is recommended that you confirm the results above with statistical software. The degrees of freedom will be 7.9809. The test statistic will be 0.7975, and the critical statistic will be 3.358. We reach the same conclusion. Also, observe the closeness of the degrees of freedom, test statistic, and critical statistic in these two calculations. This implies that our assumption of equal variances was a good assumption. We can also compare two groups but have paired treatment. Paired treatment means the two groups of data are dependent. Data is taken in pairs, with the difference calculated for each pair. Essentially, a paired treatment t-test can be treated the same as a comparison of one group to a known target. The group will be the differences between the two samples, and we will compare the average of these differences to 0. Note that the paired treatment method will often show a more significant difference because the standard deviation of the differences includes no sample-to-sample variation. As a result, the paired treatment t-test is a more sensitive test than the independent t-test. The test statistic formula consists of the mean of the differences, d bar, the standard deviation of the differences, and the number of differences, or the sample size. Let's consider this example. We measure the conductivity of a material and then subject each sample to passivation. We then measure conductivity again to see if passivation has any effect on the conductivity. Assume alpha is 0.05. When calculating the differences consistently, subtract the after measurement from the before measurement. Keep the sign if the difference is negative. The mean difference is 1.714. Standard deviation of the differences is 2.7516. Based on the size of the test stat compared to the critical stat, we fail to reject the null. The passivation treatment appears to have no effect on conductivity. Homogeneity of variances is a common assumption in many statistical tests. We also can assess the relative precision of two instruments or stability of two processes. The test we typically use for this application is the F-test. The F-test is based on the Fisher distribution created by the ratio of the variances of two normally distributed data sets. The Fisher distribution is non-symmetrical and based on numerator and denominator degrees of freedom. Each degree of freedom is determined from the respective sample size minus 1. The test statistic is just the ratio of the two variances. Let's consider this example. We have two lots of material. We are seeking to find if the variance of the material thickness is the same. Assume alpha is 0.1. Lot 1 consists of 17 samples with a standard deviation of 0.248. Lot 2 consists of 11 samples with a standard deviation of 0.198. The test statistic is the ratio of the variances. The critical stat with numerator degrees of freedom of 16 and denominator degrees of freedom of 10 with alpha of 0.1 in the right tail is 2.233. Since the test stat is smaller than the critical stat, we fail to reject the null. The two lots of material have the same variance.